This is second half of lecture 23 of EP1. In this part, I will go over 3 homework problems, and towards the end, we will talk about damped and forced oscillations. Let me start with problem 23.1 on slide number 6. What you have here is a pendulum, a rod suspended. This rod has length L from top to bottom. And if you mark the midway point here, then it's suspended not from its top, but from this point up here, which is distance x above the midpoint. The question is to find the period of oscillations, t, and to find this point x for which the period of oscillation is the least. So find t and find x that results in minimal t. Let's start with finding the period. So what we have here is an extended pendulum that we talked about in the first half. So I can just write down the formula. The formula is that my period is 2 pi times the square root of the moment of inertia divided by mgh. What we need to do now is we need to find the components that go into this formula. We need to find the moment of inertia, and we need to find this h. Let's start with the h, because that's the simplest piece. H is the distance from the pivot point to the center of mass. And this distance, we are told, is x. So we call this distance x. Even though we don't know the number itself, we can use x. So h is equal to x. Now, what about the moment of inertia? Moment of inertia of a rod, when the pivot point is exactly in the middle, is given by 1/12 of mass times length squared. This is a formula that I can find in the table. But the tricky part here is that my rod is suspended not from this point, but from this other point, distance x away. And that's not going to be in the table. So to find this new moment of inertia, what I have to do is I have to use the parallel axis theorem. So first of all, since this, if the pivot point is over here, then more of this rod's mass is away from the pivot point, which means that I expect my moment of inertia to be larger. Anyway, let's get back to the parallel axis theorem. Parallel axis theorem tells me that if I know the moment of inertia around the middle, which is 1/12 of ml squared, then I can find the moment of inertia around other points by simply adding mass times this displacement squared. So mass times x squared. If I'm distance x away from the midpoint, from the center of mass, then my moment of inertia is the moment of inertia around the center of mass plus m times this distance squared. Okay, so now I also have the moment of inertia. Let's plug both of them into my formula for the period. I will have twice pi 1/12 of ml squared plus mx squared divided by mgx. you see that mass cancels out both from above and below. So my result apparently doesn't depend on mass. Okay, so this is how my period depends on x. Now the question is, for what value of x do I have the least period? And if you know your calculus well, when they ask you to find the minimum of a function, what you do is you take the derivative of the function and you say derivative is equal to 0. That's where you have the minimal and the maximal values of the function. So what you could do is you could take this expression, which is not a nice expression, but still you could take it, you could take a derivative using a computer, and you can equate that to 0. There is one trick that will make it, could make it slightly simpler. And this trick is that instead of looking at t, you could look at t squared. So t squared is equals to 2 pi 1/12 of L squared plus x squared divided by gx. And if t is minimal, then t squared will also be minimal. So if you find the minimum of t squared, then you have found the minimum of t. And this is this makes your job slightly easier because this expression doesn't have a square root, and it's easier to take the derivative of. So let me take a derivative of t squared with respect to x. I have a ratio. Well, actually, there are two ways of doing this. What I would like to do is I will split this ratio into two terms. And then I will take derivative of each. Derivative of the first term is negative 1/12 of L squared over gx squared. And the derivative of the second term is plus 1 over g. So this has to be 0. And if this needs to be 0, then my negative 1/12 of L squared divided by gx squared plus 1g needs to be 0. I can now solve this equation for x. G will cancel out. And I will get, if I solve this, I will get x equal to L divided by the square root of 12. So this is a very interesting result. Not very intuitive. This would be hard to guess. But apparently, if you want your rod to be oscillating with the highest frequency and the least period, then what you need to do is you need to hang it 1/12 of its length above its midpoint. Now let's do the second homework problem. It's not number 2 in homework, but it's the second one on the lecture slides. That's slide number 7. So in this homework problem, you have a wall and a spring, and you have this cube that's connected to the spring. You know the size of the cube, you know its mass, and you know how stiff the spring is. Okay. So they tell you that this cube was rotated by 3 degrees, kind of like this. And if this is the pivot point, then you know what will happen. Because of the spring, you will have a restorative force, and your cube will start oscillating like so. The question is, what's the period of oscillation? So this problem is kind of hard. First, we have to think about what kind of oscillation we have. it seems to me that we have angular oscillations. So in the lectures, we had something like this, object suspended from a wire that was oscillating in the angle. This is similar, except your restorative force isn't provided by the wire, it's provided by the spring instead. So what I will do is I will look up expression for the period of angular oscillator. T is equal to twice pi square root of I over kappa. And I here is the moment of inertia of the object, and kappa is the torsion coefficient. The torsion coefficient is defined through this equation. It's torque is equal to the torsion coefficient times the angle. And the torsion coefficient basically tells you how much torque you get if you twist this thing by a unit angle. So the torsion is torque divided by the angle. The more angle you have, the more torque you have usually. So the ratio is a number, and it describes the sensitivity of your angular pendulum with respect to small angular offsets. Let me start with the moment of inertia, because that's simple. Moment of inertia of a cube. I will look it up in a table, and the table tells me that if I have a cube, and if the pivot point is exactly in the middle, then I have a moment of inertia of 1/6 of mass times the side squared. So 1/6 mass of the cube times its side squared, and that's true if I have a cube, and if my axis of rotation is pointing like this, and if it goes exactly through the middle, which is the case here. Okay, so I have my moment of inertia. Now I have to figure out what's my torsion. So to figure that out, I will draw my cube here. And I will see there is a spring here, and I will see how much torque I get if I rotate this cube by some angle theta. So I will rotate it by some angle theta. So this is the new offset position. The question that I have is, how much torque do I generate? How much torque does this spring generate? Let's see. So torque is force times distance from the axis of rotation. And in this case, distance from the axis of rotation is this distance. And this distance is equal to, let me think, what does this distance equal to? So it's half of the diagonal. Yeah, I have my cube here. I have my diagonal. If this is d and this is d, this is square root of 2 times d from the Pythagoras theorem. And so half of that would be d divided by the square root of 2. Okay, so that's how much torque I get. Now, how much force do I get? The amount of force, since this is a spring, is K of the spring, stiffness of the spring, times this delta X, times the stretching of the spring. What's delta X? I have to use geometry here. So let me redraw this. I was here. This was my equilibrium, and then I moved by angle theta. And so if I moved by angle theta, and if this was d divided by the square root of 2, then the arc is equal to the angle times the radius. So my delta x will be, this delta x will be d divided by the square root of 2 times theta. And my force, my restorative force will be K, where K is the stiffness of the spring times delta x, d times square root of 2 times theta. Okay, so let me plug this into my torque. For the torque, I have then negative k d squared divided by 2 times theta. So what's the torsion then? Torsion is defined through this equation. Torsion is, the coefficient of torsion is the coefficient between the angle and the torque. So if I write torque is equal to negative torsion times theta, and if I compare these two equations, then from here, my conclusion is that my kappa, my coefficient of torsion, is k times d squared divided by 2. Okay, so it looks like I have all the pieces that I need to compute this period. And the period is 2 pi times the square root of 1/6 m times d squared divided by k d squared divided by 2, which is the d squared cancels out. So it turns out I'm not really sensitive to the size of this cube. And what I get is I get twice pi the square root of m divided by 3 times k. Let me think. Does this make sense? It kind of makes sense. If I have a heavier cube, I will have longer period because it will be rotating slower. And if I have very stiff springs, so if this is high, then my period is low and my cube is oscillating faster. Now let's do the third problem on slide number 8, which is kind of similar, but simpler than the second problem. So hopefully this one will be easier to understand. You have a wall, you have a spring with stiffness k, and you have this rod that's fixed in its midpoint, right here. You know the mass of this rod, you know the k for the spring. The question is, if the rod is rotated slightly and then released, I mean, it's obvious that it will start oscillating. The question is, what's the period of those oscillations? So I will do exactly the same thing here. I will say this is an angular oscillation, and the formula for my period is 2 pi the square root of I divided by torsion. What's I? I in this case is simple. It's a rod fixed in the middle. So tables tell me that my I is 1/12 of mass times length squared. Now, what about the torsion? To find torsion, I will do exactly the same thing as I did before. I know that torsion is something that relates torque to the angle. So I will write down the equation for the torque, and I will try to figure out what the torsion coefficient is from there. Let me redraw this thing over here. I have my rod, and this is the midpoint. Let's say I rotated my rod by angle theta. By how much would I move? What's my delta x? Well, this side is L over 2. And for small angles, my arc length is my radius times the angle. So delta x is L over 2 times theta. Okay, so that's my delta x. This means that my force generated by the spring when I move my rod by a small angle theta is it's negative k times delta x, so it's negative k times L over 2 times theta. And now the torque is force times distance from the pivot point, and in my case it's negative k L over 2, another L over 2, so L squared over 4 times theta. And by comparing this equation to that equation, I will conclude that my torsion coefficient kappa is k times L squared divided by 4. So let's use that in here in my equation for the period. What do we have here? We have period equals to 2 pi square root of 1/12 of mass times length squared divided by k L squared divided by 4. Length will cancel out. That's good because I didn't have length given in the problem, so I was hoping it would cancel out. And then I get 2 pi times the square root of m divided by k divided by 3. So again, this makes sense. The scaling makes sense. Heavier rods will oscillate slower, and if I have a very stiff spring, then I will have small periods, so I will oscillate faster. Finally, what I want to do is I want to very briefly touch on two things that we will not have time to go in depth, discuss in depth, but I would still like you to be aware of them. And first thing is damped oscillations. So whether you have a pendulum or something on a spring or something on a wire, in real life, oscillations will always dampen with time because there is friction, there is air resistance. And this damping isn't really accounted for by the formula that we had for a simple harmonic oscillation. The formula read x is equal to a times cosine of omega t plus phi. And if you look at this formula and if you draw it, if you plot it out, you know how the cosine looks like, so it will always oscillate back and forwards without ever stopping. And obviously in real life, that's not what we have. So we have to somehow in our models, we have to account for the damping. When we had no damping, what we did was we wrote, for example, let's take the example of this spring. For the spring, the Newton's second law read F is equal to ma, but then the force was negative k times delta x. So we rewrote it as m second derivative of x is equal to negative kx. And when we solved this equation, we got the cosine as a solution. When you have damping, you have to add some extra forces here. You have to add forces of damping. And depending on what kind of forces you have, you will get different equations and different solutions. Usually, in many cases, you have damping forces that are proportional to velocity. So if you are moving faster, there is more damping than if you're moving slower. So these damping forces usually, in many cases, depend on your velocity. And so you would have an extra term here that's proportional to the velocity, some number b times v. And velocity is, of course, derivative of x. So the differential equation that describes your motion will now look like this. When you learn, or if you already learned differential equations, you will find that this equation isn't actually that difficult to solve. I don't want to get into technical details here in EP1, but the solution of this equation is given by x is equal to a times the exponential of negative b t divided by 2m times the cosine of some frequency times t plus 5. And if you want to verify that this is a solution, take its derivative, take its second derivative, plug them in here, and you will see that this equation will be satisfied by this solution. Now let's look at this equation and let's see what happened here. How is it different from the solution that we had before? So before we considered damping, we had this equation. And one big difference between damping and no damping is that you now get this exponential term here. Exponentials, we all know how the exponentials behave. Exponential of negative t is looks like this. It gets smaller and smaller with time. So if you have a product of the exponential and the cosine, then this is how the cosine looks like. This is how the exponential looks like. Their product will look something like this. You will have your cosine, but its amplitude will be decreasing with time. This is the effect of the exponential. And this makes sense from physics point of view. This is exactly what you expect. You expect your oscillations to continue, but your amplitude to decrease with time. I think you have one problem about damping in your homework. For that problem, all you will have to do is you will have to look at this equation, and you will have to interpret these terms. So basically two differences. One difference is that you get an exponential that damps you. And the second difference is that your omega isn't the same. Your new frequency, instead of being square root of k over m, your new frequency is square root of k over m minus b squared divided by 4 times m squared. So your frequency goes down compared to a non-damped case. When you didn't have damping, you just had this. And with damping, you're subtracting something from your frequency. So if your undamped oscillations look like so, your damped oscillations will have a slightly lower frequency, which means that if you put them on top of each other, damped oscillation will have a slightly higher period. So this is all we need to know about damped oscillations for now. Basically, this is the formula, and this formula has one extra term that has a clear meaning. It just reduces your amplitude exponentially with time. Now, if we only had damping, then all our oscillations would eventually die out. In real life, in addition to damping, very often we have driving forces. So if you have a pendulum, let's say this pendulum is a swing, and you have a child sitting on a swing. If there is someone here who is pushing this child, then even though you have damping, these oscillations could in principle continue forever. Because we have a force, external force applied here, and this external force replenishes energy that's lost to damping. For the driven oscillations, we're not gonna write down any formulas. Those are kind of a bit too complicated for this class. But there is one thing that I would like you to be aware of. You have one homework problem on this, and this is the phenomenon of resonance. So resonance is without equations, it's very easy to understand. Let's again look at the pendulum. Let's say you have this pendulum, and it's swinging up and down, left and right, like this. then we know that the frequency of this pendulum is given by, the period is given by square root of its, is it length over g or is it g over length? I have, it's L over J. I have shorter period if I have stronger gravity. Yeah, okay, it's L over J. So this is your period. And if you just left this pendulum alone, with if there was no external force whatsoever, then this pendulum would forever happily oscillate with this period. Now the question is, if I'm applying a force, if I'm pushing this pendulum at some times, then does it matter how I apply this force? And the answer to this question is that it does matter how I apply this force. And it's not very surprising. It turns out that my force is most effective in supporting this pendulum if the period of my force matches exactly the period of this oscillation. Which means that if this pendulum takes, say, 2 seconds to swing back and forth, if I push it once every 2 seconds, that's the most effective way of transferring my energy into pendulum's energy. Instead, if I keep pushing it at random times, let's say I push it once every second, so what will happen if I push it once every second? So my pendulum is here. I pushed it in the beginning at time 0. The period of oscillations is 2 seconds, which means that in 1 second, this pendulum will be over here. And if I'm pushing it once every second, then when my pendulum is here, I would push it again. And this is obviously not very optimal because my pendulum was just about to turn back and I pushed it at the wrong time. You can think about other cases. For example, what happens if I push my pendulum once every 1.5 seconds? If I push it once every 1.5 seconds, I would be pushing it here, and then it would go forward in 1 second, and it would come back here in 1.5 seconds. And I would be pushing it here, where again it's not very optimal. You know, I'm kind of slowing down the motion. Now this is a very hand-wavy, non-rigorous explanation, but nevertheless, I think it's easy to understand what I'm trying to get at. If you have an external driving force, which is periodic, it's best if the period of your force is in sync with the period of natural oscillations. There is this plot in your on slide number 10 that shows what happens to the amplitude if you apply of an oscillator, if you apply an external force with some random frequency. So this is, the midpoint is the natural frequency of your oscillator, and this vertical axis is the amplitude of oscillations that you get. And the lines on this figure kind of look like this. And these lines tell you how big of an amplitude you get if your external force has a certain frequency. And so you see that if, since this line peaks at the natural frequency of the oscillator, you see that you will get most amplitude if you push your oscillator exactly with the period, its natural period. If you push it with a period that's less or more, you will get less amplitude because you are less successful in synchronously transferring your energy to the oscillator. Sometimes you're helping it, sometimes you're not helping it. So the overall amplitude is low. This is the end of the second half of lecture 23. This is the lecture that's, this is the week, the oscillations week, that's arguably more difficult than other modules that we had before. Since I have only 50 minutes, it's difficult for me to explain everything in detail. So what you need to do is you need to join Zoom help room sessions on Monday, Wednesday, and Friday. You need to tell me that you didn't understand something, this or that, and then we will have a conversation. And when you have a conversation, it's easier to understand things. Thank you and good luck on your exam on Friday.